Our weather is constantly changing because the winds are always moving. All planets with atmospheres have winds, depending on how much energy they receive from the Sun. This is Jupiter. We're going to see why the Earth and other planets have bands of steady winds. In this video, we will see the principles of atmospheric circulation, which is the basis for our everyday weather. However, there are so many factors affecting weather, and they keep changing. Even though we understand the principles, forecasting the weather several days ahead is often very difficult. The Sun provides all of the energy leading to changes in our weather. Without solar energy, the air that surrounds the Earth would remain still. The Sun's energy reaches the Earth's surface unevenly, and this causes the atmosphere to move as wind. At the equator, sunlight hits the Earth directly. The energy falls at a constant rate of around 1 kilowatt per square meter. Towards the poles, the sunlight hits the surface at an angle, and there is less heating because it is spread over a larger area. Also, at this lower angle, more of the sunlight is reflected from the oceans and from ice. Clouds also affect some of the sun's energy. Clouds shade the Earth and so keep our atmosphere cool. In fact, about 30% of the solar radiation is reflected back into space. The air in our atmosphere is warm, and we bathe in it like a warm bath. It stops the shadows becoming too cold. On the Moon, where there's no atmosphere, warmth arrives only from the sunlight. In the Sun, the rock reaches about 100 degrees Celsius. While in the shadow, the rock will be 170 degrees below freezing. Sunlight warms the surface of the Earth, which then radiates at the infrared wavelength up into the atmosphere. Some of this infrared radiation is absorbed by water vapor, carbon dioxide, methane, and other gases in the atmosphere, causing it to warm. Eventually, all the infrared radiation goes back out into space, but these greenhouse gases, as they are called, have slowed it down. This is called the greenhouse effect. Without the greenhouse gases, our average temperature would be minus 18 degrees Celsius. With the greenhouse gases, the average temperature is plus 15 degrees. Venus has an atmosphere high in carbon dioxide, and the temperature is hot enough to melt lead. As well as radiation, the air nearest to the warm surface is heated by physical contact. So, our atmosphere tends to be hotter near the ground. The warm air then rises and warms the atmosphere by convection. Also, when the sun evaporates water, the vapor takes energy into the atmosphere, This energy is released when the vapor condenses to form clouds. Eventually, all the heat is radiated back into space. If it wasn't, the Earth would continue to get hotter. Next, we'll see how temperature variation affects atmospheric circulation. Watching a flame, we can see that hot air rises. This balloon rises because its hot air has expanded, pushing some air out, making the volume of air lighter than before. It floats upwards, like a cork in water. Where air is heated, it expands and then rises. This is called convection. When this happens, we get a pocket of low air pressure. Air flows inward to replace the rising air. Cold air is heavier and sinks. We can often feel cold air flowing down a hill or valley in the evening. In a similar way, when air is cooled, it becomes heavier and forms a high-pressure cell. Air flows outwards from this system. On Earth, air flowing from high to low pressure zones is wind. But here the story becomes more complicated. Because of the Earth's rotation, no wind can move in a straight line over a long distance. From what we've seen, we'd expect cold air at the poles to sink, flowing away from the poles, while warm air rose at the tropics, forming a wind pattern like this. But it's not that simple. By trying to rule a straight line on a spinning sphere, we can see what happens when the wind's momentum tries to take it straight to the equator. The Earth moves under it, and the path from the Earth's point of view appears curved. This is known as the Coriolis effect. Like the water in this bucket, our atmosphere has inertia. We can see that if the bucket changes its spin, the water at first stays where it is. It will take time and the help of friction for the water to pick up the spin of the bucket. Using two plastic hemispheres, the inner one representing the Earth and the outer doing the job of gravity, holds the atmosphere in place. We'll pour water into this hole. This small camera moves with the Earth as it spins. Like cold air, the water in our model flows from Antarctica towards the equator. As the globe spins, the water does not at first pick up the spin of the globe. The Earth moves underneath the atmosphere. And again, amongst the chaos, we can see a lot of the confetti staying where it is. This is an unusual viewpoint. In real life, we view it from the Earth's surface. The small camera shows the view. The wind appears to be rushing over the surface. Actually, the water hardly moves at all. The globe is spinning under it. Gradually, friction drags the atmosphere to the speed of the surface. And from the geocentric viewpoint, the confetti at first appears to stand still. Let's look at that again. At first, the water doesn't spin. It's pushed upwards while the Earth moves along under it. From on the Earth, it looks as if the wind is blowing over the surface. It's hard to know whether the air is rushing past us or we are speeding along below it. Usually, it's a bit of both. So due to inertia, winds coming from the poles are deflected. They end up spinning around the polar regions. For this reason, Antarctica has mainly easterly winds. It is the windiest place on Earth, while the equator is relatively calm and still. Here, the hot air rises high into the atmosphere and is pushed towards the poles. Different parts of the Earth's surface are traveling at different speeds. At the equator, the surface and the air are traveling at 1,600 kilometers per hour. Further away, at 30 degrees from the equator, it is traveling at 1,400 kilometers per hour. And at the poles, the speed is 0. If air from the equator, which is traveling at 1,000 miles per hour, or 1,600 kilometers per hour, is pushed towards a region where the Earth is slower, then the air will overtake the surface and will end up heading east. It does not reach the poles, so the airflow is like this. These donuts are called Hadley cells, and the air tends to circulate within them. At the poles, cold air forms a pressure cell called a polar pressure cell. Air flows towards the faster traveling equator, but drops behind this time because it is slower than the surface it is moving towards. So again, it is diverted by Coriolis. Let's look at the region between the cells. It's quite complex here, but we'll try to simplify it. In the upper atmosphere, as the air from the equator heads towards the poles, it squeezes into a smaller area. Air builds up, producing a high pressure belt on the surface at about 30 degrees from the equator. At the surface, air is diverted both north and south. Air heading towards the poles is also deflected. These winds are called westerlies because winds are traditionally named according to the direction they come from. Ships sailing past Africa found the winds helped them on their journey to the East Indies and Australia. These westerly winds are the reason Cape Horn is so stormy. Because they're found at 40 degrees latitude, they are known as the Roaring Forties, but only in the southern hemisphere. At 60 degrees latitude, westerly winds meet the cold polar easterly winds in a collision zone known as the polar front. The relatively warm, moist westerly air rises above the cold polar air, producing a belt of storms. This satellite image shows the storm belts of these polar fronts. Rising moist air at the equator also produces cloud. At 30 degrees from the equator, the air is sinking. It compresses, becoming warmer, meaning it is more capable of evaporating water. So most deserts are found about 30 degrees from the equator. High pressure systems form over the oceans in this region, and this means very calm, clear weather. In the 15th century, European settlers heading for the New World were often becalmed here, sometimes running out of food for their horses. The dead horses were cast overboard, leading to the name horse latitudes. Air moving from the horse latitudes towards the equator produces steady winds called trade winds. They were so named because sailors could rely on them to speed them on to the West Indies for trade. The low-pressure zone around the equator where the winds meet is called the Intertropical Convergence Zone or Equatorial Trough. All of these winds and air pressure systems form what is known as a general circulation of the atmosphere. It consists of 7 alternating surface belts of high and low air pressure. In between these are the 3 major wind belts of each hemisphere. On Jupiter, we can see a similar pattern of wind belts caused by Coriolis. Because it is larger, there are more of them. On Earth, we have seasons because the axis is tilted at 23.5 degrees. In this model, the Earth isn't spinning and the Sun is smaller and closer in. Here, we're showing what happens during winter in the Northern Hemisphere. Three months later, sunlight falls equally on both hemispheres. The days and nights are the same length. This is known as the equinox. In June, it's summer in the Northern Hemisphere and winter in Australia. 3 months later, another equinox, and it's the middle of spring or autumn. So as the Earth changes its angle to the Sun, the seasons change. The various pressure belts stay aligned with the Sun as the Earth orbits. To us on the surface, the pressure belts appear to move north and south seasonally. Monsoons are seasonally reversing tropical winds. They bring the wet and dry seasons to the tropics. They are essential to agriculture in these regions, especially Asia. We have seen that the trade winds move towards the equatorial trough or intertropical convergence zone. This zone moves north and south depending on the season. Where these lines are furthest apart, there are distinct wet and dry seasons. This is most marked between southern Asia and northern Australia. In December-January, the trade winds have to cross the equator to flow into the equatorial trough. Coriolis force deflects wind coming from the equator. These become the northwest monsoon over Australia. In June, July, it is the reverse. The equatorial trough has moved north. Again, the trade wind swings around as it crosses the equator, becoming the southwest monsoon into Asia. The monsoons happen in Africa and less in South America. They are most intense in Asia, which has the largest landmass, building up an intense low-pressure system each summer. The Himalayan mountains cause the equatorial trough to move much further north than anywhere else in the world. As air flows north, it picks up moisture from the Indian Ocean. So the monsoons bring torrential rain to Asia in July. In order to predict the movement of winds, meteorologists need to measure the air pressures that drive them. pressure is usually measured in hectopascals, and when mapped, produces a synoptic chart. These pressures are recorded and collated by weather services all over the world. On a synoptic chart, isobar lines link areas of the same pressure. ISO means the same, and bar is short for barometric pressure. Isobars are like contour lines. The hills are high pressure and the valleys are low pressure. You can tell them apart by reading the numbers. This is a low-pressure system in the Northern Hemisphere. Air spirals into it because of Coriolis and is named a cyclone. Using time-lapse satellite images, we can watch the cyclone form, like this one heading for Japan. High-pressure systems are called anticyclones because air spirals outwards. The direction of wind flow in cyclones and anticyclones depends on which hemisphere they are in. Air flowing from high to low pressure systems is deflected by Coriolis, producing spiraling winds like this. We've seen some of the forces shaping our weather. However, the outlook is complicated by turbulence and chaos. Even with sophisticated forecasting equipment, it's still a challenge to predict our weather very far ahead.